Hi everyone, this is Madhav. Welcome to Projectile Motion. This is still kinematics, basically the last kinematics we're gonna do before we move on to some more complicated content. Though I did want to talk about this because it really is one of the more simple examples of an important idea in physics, which in a fancy terms is called reductionism, but in simple terms is called make things simple or simpler. So in this case, you see we have a projectile. I'm assuming you know the basics of projectile motion. I'll, as ever, link to resources in the description below if you don't. But what you can see in this GIF here, which is not mine, I don't know exactly who to source for this because it's all over the internet. What you can see in this GIF here is that this cannon is launching this ball off a cliff, and these different arrows represent the different vectors. You know, one in the x direction, one in the y direction. You see that the arrow in the x direction, it just always stays the same. The velocity in the x direction, it's always 60. But when it comes to the arrow in the y direction, you see it starts off large in the positive direction, it gets to 0, and then it starts going down. And that's because you have acceleration in the y direction because of gravity. So when it comes to analyzing projectile motion, we don't want to worry about, you know, this weird parabolic trajectory thing. We just want to focus on one direction at a time. And when it comes to one direction at a time, we can see that in the x direction, no change in motion occurs. In the y direction, you just have linear acceleration due to gravity. So we took complicated motion in like a weird curve, and then we broke it down into just, you know, two directions, and now it's simple. So with that theory out of the way, with that philosophy out of the way, let's take a look at a problem. Came up with this myself because I don't know, all the projectile motions I find in textbook, they are usually about cannonballs and cliffs, and I'm kind of tired of cannonballs and cliffs. Anyways, you can, you know, read the problem yourself. As ever, I will note I'm using this notation. It just means meters per second instead of like whatever fancy scripts, but whatever. Anyways, let's get going. We're going to use the same process as in the last video. We're going to draw a picture. We're going to state our assumptions and variables. As a subnote here that I didn't include last time, we also want to make sure that we include what is given to us versus what we need to find, what's required. Then we're going to make a table of equations as ever, and we're gonna just solve the equations and state our solution. Cool? Alright, pretty standard. Let's get to it. Let me get our picture tool ready. And we're always gonna use a dark background because dark mode, that's, you know, what we do. Anyways, let me draw out this situation. So hopefully you had a chance to read the problem here. Just gonna draw that out. So we have a person over here. They just threw a ball on a trajectory like so. That looks a little bit weird, but whatever, it's close enough. So they threw this ball in this trajectory. The ball started at the initial height of hi, which is not the same as the height of the person, just the height of the ball. And at the end it touches the ground, so hf is equal to 0. In that time, it traveled some distance, which I'll label SB for the distance of the ball. And we have a heroic fielder or something, some other person over here who was initially standing behind this person, and they're just like hauling it. They're sprinting as hard as they can, starting from rest and then accelerating with a velocity, accelerating with an acceleration of AA for, person A. Initially there were some distance SA away from, this other person, and starting from rest they accelerate all the way over to just barely catch the ball in time. So I just dove in heroically and got the ball right before it hits the ground, when the final velocity is the final height is about 0. So here's our situation. Let's take this image and move it over here. Here we are. Just gonna crop the image a little bit. One thing I forgot to do in the image is declare a positive and negative axis, so I'm just gonna add that in. So we're gonna define up to be positive and right to be positive. This is the positive x, this is the positive y. There we are. Now we can state any assumptions and variables. So I'm going to do the assumptions first. As ever, if we want to use kinematics equations, which we will, because that's the kind of motion we just saw here. One direction velocity doesn't change, the other direction there's constant acceleration. So we have to assume, constant acceleration so that we can use our kinematics equations. Let's assume no air resistance. Do we need to assume anything else? I think this is a good start. Let's write down our given variables. So we know the initial velocity of person A, which we will call VAI, is 0. We know that HI is 1 meter from the problem above. Baseball is thrown 1 meter above the ground. Another thing that I forgot to put in is this angle theta, so I'm just going to label it here, and we can pretend that, whoops, we can pretend that error never happened. So this is an angle theta, and this is the velocity of the ball initially. I'm just drawing it very long so that you can see it straight. It's not like a curved velocity. So this is VBI, this velocity, and VBI is in this direction. It's not horizontal, it's not vertical, it's in this diagonal direction. So we can say that theta is equal to 30 degrees. If anyone knows a shortcut for the degree symbol on Google Docs, let me know. I would much appreciate it. Anyways, yeah, theta is 30 degrees, VBI in that direction, it's 20 meters per second. 20 meters per second. we know that SA is equal to 10 meters because the second player, A, is originally 10 meters behind the first one. Don't know what SB is. We know that HF equals 0. Alright. Anything we missed? I don't think so. Alright. Let's state our required variable. So we're looking for the acceleration AA. Cool. And let's finally define, we created this variable and didn't explain it. Define SB to be the distance that the ball travels before hitting the ground, barely hitting the ground before it gets caught. And we can say let t be the time between the ball being thrown and being caught. You don't always need to define these things. Sometimes, especially if you're in a school setting, writing a test or something, it's evident. But just for now, it's nice practice. Now, we're going to start creating a table of equations. So, this is the last physics part, and then we're done. Yay! I'm gonna start off with 6 equations for now, and then we can add more if we need. Remember, we're just brainstorming right now. We don't need to find the perfect equations. Just like start listing equations, and we'll know when to stop based on how many equations we have versus how many unknowns we have. We want to have at least as many equations as unknowns. Here, you'll see the advantage of having a table of equations instead of a mess, because we have these different objects, right? We have a person moving, we have a ball moving, and we have different directions, x and y directions. So equation 1, let it relate to the person A. We'll just say that the final velocity, VAF, is equal to the initial velocity of this person plus their acceleration over time. Do we need any other equations for this person? We have this equation about the distance they travel, so why don't we also add that in? We know that the distance they travel, which is going to be SA and SB, right? They have to cover both of that. They have to catch up with the ball. They have to cover both of these distances. So we know that the distance that they travel, I think the kinematics formula here is, it's going to be VAIT plus 1/2 AAT. Let's just double check that so that I'm not feeding you misinformation. Yep, looks right. So now we're going to move on to the ball. Well, that should have been equation 2. There we are. Now we're going to move on to the ball. Let's focus on the y-axis first. So in the y-axis, first we need to figure out, like, what is the velocity of the ball in the y-axis? We don't even know that. To do this, I'm going to draw a diagram, because I hate when people skip this step. When I was first doing physics, like, I always got confused with where people got these expressions from. So let's not skip steps here. I'm going to draw out a quick kinematics diagram, not a kinematics diagram, a quick trigonometric diagram to show this. So the ball has an initial velocity like this, right? VBI. And it makes an angle of 30 degrees with the horizontal. So let that be theta. We want to figure out what is the vertical part of this velocity vector and what is the horizontal part. So we want VB xi, not a lot of subscripts there, and VB yi. We can do this using just basic trigonometry. So this is a triangle, it's a right triangle. Make sure you know that, even though it doesn't look right, whatever. We can see from this triangle that sine of theta, it's equal to VByi over VBI. Cos of theta, it's going to be equal to this side over this side. Using these two, we can isolate for the parts we want. The parts we want are just VByi and VBxi. We want the velocity in the y direction and the x direction. So if we just multiply both of these equations by VBI on both sides, we get what we want. We will get that VByi, it's equal to VBI times sine theta. And VBxi, it's equal to VBI cos theta. So people usually just skip to these steps over here. I just wanted to write it out one time before I started skipping to that step, because like it always confused me at the beginning. So there you go. After this I'll just do it in my head, but this is what I'm doing in my head, if you're ever wondering like how did he get that equation. So I'm just going to write out what we just identified. VByi is equal to VBI sine theta. And in the x-axis, we have VBxi, it's equal to VBI cos theta. Let's keep on creating more equations. So in the x direction, we don't need any kinematics equations because the velocity is always the same, right? In the y direction, however, we do need equations. So in the y direction, we have a height h, right? And we know that the velocity, it has the acceleration of gravity acting on it. That's the only acceleration. So that's the equation we're going to write. Again, I hope I'm getting this right, but hf minus hi, it's equal to VByi t plus frac. That's just the shortcut for fraction. We know what the acceleration of the ball is. As I said, it's just gravity, but for now I'll write AB for the acceleration of the ball. We need a t squared here, we need a t squared here, so let me just fix that. And then the other equation we could write, well, I am really not numbering these equations well today. So now, finally, I want to do one last thing here. We have our 5 equations, but just want to precisely define out that the acceleration AB is different from AA, right? And let's make sure we don't forget that. In the picture, we can see that the AB, the vertical acceleration, is just the acceleration of gravity. And I defined up to be the positive axis, if you remember my diagram, so this is going to be a negative acceleration. Now, I think we're ready to solve. So here's the general strategy that usually tends to come out with the projectile motion problems that you'll usually see. You see this equation about, well, these two equations about the ball's motion in the y direction. It usually works out that you're given enough information to only have time as the only unknown variable, right? Because, like, okay, we have the distances given to us. VBY, we just calculated up here. AB, down here, so time is the only unknown. So, initially, it's usually a good idea to focus on the y motion of the ball, calculate how long does it take, because while the y motion is happening, as we saw, the x motion is still going on. So the time that we solve for down here, well, we're going to reuse it for these equations later, which is going to help us find our solution. So let's use that strategy. We're going to focus on the y motion first and solve for time with these equations. So substitute, we want to substitute 6, and we want to substitute 3, right? 6 and 3 into 5. So making those substitutions here, we have this turns into minus g instead of plus AB. Oops. And remember, g is a constant that we know, gravitational constant, 9 equals negative 9.81. VBY, I, it's going to be VBI sine theta. We know what theta is, we know what VBI is, so we're good there. Now we can just solve for this using quadratic formula. So let's isolate on one side so this becomes a little bit neater. So we have 1/2 gt squared, where this part is like a coefficient in front of the t squared term. And then we have minus VBI sine theta, which is the coefficient in terms of the t term. If you don't see what I'm doing, I just added 1/2 gt squared to both sides of the equation, subtracted this from both sides of the equation, and then just left these constant terms at the end, so that we have an equation which we're ready to use the quadratic formula on. People might get confused if I do this in algebraic form, so I'm just going to substitute in raw values in order to use the quadratic formula. So we're going to have 9.81 over 2. Here, be careful, you want to substitute in 9.81, not negative 9.81, because you already took care of the negative sign in the equation. You can't double up, do one or the other, not both. So that's a numerical value we can use. This over here, it's going to be 20 sine 30 degrees, which is a numerical value we can use. And over here we have plus, so 0 minus 1, so that's just going to be minus 1. What's sine 30 degrees? 1/2. Okay, so you can type it into Google if you don't believe me. Oh, maybe you shouldn't believe me, it's not 1/2. I'm pretty sure it's supposed to be 1/2. Is that in radians? Yeah, it's 1/2. Google lying to me. Anyways, so it's going to be 20 times 1/2, which is just going to be 10. That's looking more quadratic equation like, right? 9.181 over 2. What is this going to be? It's going to be 4.5 plus 0.405. So that's 4.905, I think. Fact check. 9.81 over 2. Yeah. Alright. And then the quadratic formula just becomes t is equal to negative b, so negative of negative 10 is positive 10, plus or minus the square roots of negative 10 squared is 100, minus 4 times 4.905 times negative 1. So that's just gonna turn this into a plus sign. We go down here and we have 2 times 9.81 over 2. So 2 c dots, that's just the shortcut for the multiplication sign. 2 times 4.905, which is 9.81. If we plug this into a calculator, like Desmos, we're going to see that there's a darn it, Desmos, why? Okay, 10 plus the square root of 100 plus what is it, 4 times 4.905, is that it? Yep, all over 9.81. So you see one of the answers is positive. That seems reasonable. Time is supposed to be positive. 2.13 seconds. Or the other answer is negative, which doesn't seem very reasonable. We can't have negative time. So we're going to just scrap this answer. We're just going to take the positive one. Alright, we're done with the bolt's motion in the y direction. As we talked about at the beginning, now we can just take that, apply it to the x direction. So what do we want to do here? One thing I want to do is, this is 0, right? The person starts from rest. So I'm just going to get rid of this so I can simplify my life. We don't know SB, and we don't know AA, we don't know AA, we don't know VAF, we don't know the final velocity. I think what we need is a new equation here. So let's create a new equation. How do I know I need a new equation? Because I have 1, 2, 3 unknowns, but only 2 equations. So I must, I need a new equation. Let's try and find SB. So this we're going to do as SB, it's equal to velocity over time, right? So VBX is equal to SB divided by T. There we are. Now we should be good. So now we have AA missing, SB missing, and VAF. However, we have 1, 2, 3 equations. So I think we're ready to finish our solution. Okay, so let's take the equations we have. So we have 7, substitute, actually let's isolate 7 for SB, so that we can, substitute the equation we get up here. So we're going to isolate 7 for SB. We have SB equals VBX times time. We just multiplied by time on both sides. Let's call this equation, okay, first let's call the time expression, let's call this equation 8, and let's call this equation 9. Cool. We can substitute this here. Are we ready for that? I think so. Okay. Let's isolate 2 for AA. That's what we want, right? So isolate, that's the variable we were solving for, the required variable. Isolate 2 for AA. Okay, so just take the initial expression. First off, we're gonna want to multiply both sides by 2 so that we can't. Thank you, Google Docs, that's what I wanted. We're gonna multiply both sides by 2 because we want to cancel out the 1/2. We know that time is not equal to 0 because, you know, here's the time. So we are allowed to divide by t squared. If time was 0, then we wouldn't be able to. So we divided on both sides. Well, we'll call this equation 10. And now for the final solution, we have to substitute 9 and 8 into 10. So we have here as b, it's going to be equal to VBX times time. We can see this from this equation. We see that we're good to go because we still have AA on one side and then everything else is on the other side. So let's just substitute in we need to substitute in 8, the expression for time, and VBXI, which is equation 4. Right. Yeah. So substitute that above, and we have finally AA, it's equal to 2 times SA. SA was given to us as 10 meters, plus VBX, which is the same, I should specify, VBX is the same as VBXI, because like the ball's x velocity never changes, right? So VBX, it's gonna be this stuff here, 20 cos theta. 20 cos theta we know is 30 degrees. I'm gonna copy the degree symbol because I can't be bothered. There we are. And we need to multiply this by time. We know that time is 2.13 seconds. And then we're going to divide by time squared. So 2.13 squared. Type all this into a calculator and make sure you don't take the rounded value, right? We want to take the most accurate value possible. So in Desmos, what I can do is I can actually just take t, I can set that to a variable, which is why I like Desmos. And then I can take all of the rest of this business, 210 plus 20 cos 30, 2 times 10 plus 20 cos 30 degrees. Another thing we want to check while doing this, let's see the calculator is in degrees mode. Yes, cos 90 is equal to cos of 90 degrees is equal to 0. Do we have other stuff? We need to multiply this by 2.13 but that's actually t, right? So multiply this by t and then divide by t squared, and it gets us our acceleration as 20.621. Let's write that in. Equals 20.621 meters per second. Yes, I'm aware, second squared, whoops. Yes, I'm aware that this is not scientific. I did not follow sig fig best practices, but whatever. Okay, let's state our solution. The player A must accelerate at this acceleration to catch the ball. Okay, so this was a little bit of a more involved problem, but with the key ingredients, you saw that we were able to figure it out, right? The key ingredients from last time, which were to draw a picture, to state some assumptions and variables, to brainstorm a table of equations, and then the messy solution part as ever, math. Ugh. Anyways, as usual, if you feel too scared about this problem, remember, you just need to get to this part and then you'll get, just these steps, you'll get most of the points in any academic setting, and also you're understanding the physics after these steps. This is just math. So hopefully you see the key theme is break the problem down into different axes, into different objects, and that simplifies your life. And in any projectile motion problem, start with the projectile's vertical motion, then move on to its horizontal motion, and in this case we also had to move on to some other object's motion after that. Hopefully not too confusing. I'll see you next time with now forces.